In the flexibility matrix method structure approach, we are going to see an example of a portal frame, an unsymmetrical portal frame like that. So in this, the two columns are having length 10 meter and 5 meter, and let the moment of inertia of this is 4i and this is say I. The moment of inertia of the beam is 4i, length is 10 meter, and the only load over here is a lateral load of 11.2 kilonewton. Now, to analyze the structure and to draw the bending moment diagram, the first step in a force method is to find out the degree of static indeterminacy, that is ds. To find out ds, ds will be equal to, we did that several times, that is going to be equal to 3 over here. That is, if we remove 3 number of forces, 3 number of internal forces or reactions from this, the structure will become statically determinate. And that is what is done in this structure. The 3 forces, say the reactions here, this support are released or they are removed, and structure coordinates are assumed corresponding to each of these removed forces. So we have a coordinate horizontal like 1, and we have a coordinate vertical say 2, and we have a coordinate say moment here as 3. These 3 are the structure coordinates and drawn on a release structure. Now we have to develop the delta vector, delta L vector, and this delta matrix. Delta vector will contain 3 components. The applied displacements or support movements corresponding to coordinates 1, 2 and 3. They are zeros. Since this support does not undergo any yielding, the displacements corresponding to 1, 2 and 3 are zeros. So delta contains 3 zeros. Delta L. Delta L1 will be the displacement corresponding to this coordinate due to the externally applied force in a release structure like this. Delta L2 will be displacement along this direction due to the externally applied force in a release structure. Now we can find out these deltas using the unit load method. In the unit load method, as we have discussed in the section for unit load method earlier, delta L1 can be given by integral over the length of the element, length of the beam or the frame, capital M, small m, dx divided by EI, where capital M is the bending moment in a particular section, in a portion due to externally applied forces. Small m will be the bending moment at the same section due to a unit point force applied corresponding to the coordinate in question, and Young's modulus and moment of inertia for that particular portion. So delta L1 specifically will be capital M due to externally applied forces in the release structure into M1, which is the bending moment in a portion at a section due to unit point force applied along say coordinate number 1. Now we find out capital M, small m1 and further small m2, small m3, which are the bending moments at a section due to unit point forces applied corresponding to coordinates 2 and 3 in this picture. They are going to be found out using this table. Before going to the table, let me further elaborate on delta L2 and delta L3. Delta L2 will be given by integral over the length of the portions, capital M, small m2, dx divided by EI, and delta L3 would be integral over length L of the portions, capital M, small m3, dx divided by EI. We can find out them, and after that we are required to develop the flexibility structure flexibility matrix. And structure flexibility matrix will be having a size of 3 by 3 in this case, because the structure coordinates here are 3 in number. So we will be having coefficients like delta 11, delta 12, delta 13, delta 21, 22, 23, 31, 32, 33, 9 components, which is going to be symmetric. So the first one would be given by delta 11 is equal to integral over the length of the portions small m1 in place of capital M and small m1 in place of small m, that is small m1 square into dx divided by ei. Delta 12 will be equal to delta 21 will be integral over the length of the portions small m1 into small m2 dx divided by ei. Capital M will give way to small m1 and small m1 will give way to small m2 over here, like that. Like that you can find out the flexibility matrix coefficients, all the flexibility matrix coefficients. Now before doing that, we have to find out what is capital M, what is small m1, small m2 and small m3. For that we use this table. Now here the first column is for the portions. We have 3 portions here. One is DC, second is CB and third is BA. They are given here. The moment of inertia or second moment of area of cross sections are given in the second column, I, 4I and 4I. Origin of coordinates for integration. This point is the origin for this portion, C is the origin for this portion and B is the origin for the third portion, D, C and B. And limits of integration 0 to 5 here, 0 to 10 here and 0 to 10 here, as given there. Now the bending moment. The load is acting here, that has effect only in this portion. It will just push the beam and the other portion to the right side. Well, the bending moment due to this force in portions DC and CB in the release structure would be 0, as given here. If you draw the free body diagram of this structure with the external load, you are going to get 0 force over here and here, and the bending moment due to the force here in this BA portion would be that load into X. X is measured from this point downwards. That is why we have 0 here for portions DC and CB, and further minus 11.2 into X. The minus sign is because this force is hogging this particular member. That is, it is bending this member inwards like that. Convexity outside. Now small m1 will be given by applying a unit point force corresponding to coordinate number 1, like this figure. So when you apply a unit point force over here, the free body diagram would look like a force here equal to 1 for equilibrium, force equilibrium. Now a moment at this end equal to 1 into 5 for equilibrium. When we transfer that to the beam, this will be equal to 1. This clockwise moment will give way to anti-clockwise moment over here. This is 5. Further, on this end, we are going to have a leftward 1 for equilibrium and a clockwise 5 for equilibrium of forces. When we transfer that to the other column, this force will be transferred as an opposite force equal to 1, and the reaction of that would be over here, which will be 1 again. This moment is going to be transferred as an anti-clockwise moment, and for equilibrium sigma m is equal to 0 in this will be having a moment 5 to equilibrate clockwise over here, and these two forces, they produce a moment of 1 into 10, say 10 clockwise. So we require a 10 anti-clockwise for equilibrium. And we have a 5 clockwise over here and 10 anti-clockwise. So the net result is going to be 5 anti-clockwise. That is the free body diagram of the individual portions of the frame. Now M1, if this point is the origin, that is D, this point is C, distant x away in the portion will be 1 into x, which is sagging. The bending would be like convexity inwards. So a sagging moment 1 into x equal to x. M1 in the portion CB would be this moment 5, that is constant throughout the member. That is why 5 sagging in the member CB. And when you come to this member, origin is at point B, so this is x. Moment of these forces at this section would be 5, which is sagging, and 1 into x, which will be hogging. That is why 5 minus x. Sagging is taken as positive and hogging is taken as negative. That is M1. Now for M2, we can draw similar free body diagram by applying a unit force over here corresponding to coordinate number 2. And if you do that for that frame, you are going to get 0, x and 10 as the bending moments corresponding to the portions BC, CB and BA. And further, when we apply a unit couple corresponding to 3, when unit force along 1 and 2 are zeros, we are going to get a bending moment of hogging 1 in CD, BC and A as given here. So minus 1, minus 1, minus 1, minus stands for hogging. Right. So that is the table, and using the table now we can calculate all these quantities: delta L1, delta L2, delta L3, this coefficients delta 11, delta 12, and further delta 13, delta 22, delta 23, and so on. So we are going to get finally delta L vector is equal to one by EI (233.33), that is minus 1400 and 140. Delta matrix will be 1 by EI (125), 62.5, minus 25, 62.5, of course, symmetry, 333.33, minus 37.5. This number is minus 25. This number is minus 37.5. And the last number would be 10. So we have the displacement vector due to externally applied forces corresponding to structure coordinates, delta matrix, and this delta vector are in place. Now we can go for solution of this R from this equation, and we are going to get, once you solve this equation, we are going to get either using simultaneous equations or by inverting the matrix delta, we are going to get R equal to minus 7.68, 3.29 and minus 20.86. So the reactions corresponding to coordinate 1 would be 7.68 to the left. Reaction corresponding to coordinate 2 would be 3.29 upwards itself, and the reaction corresponding to 3 would be 20.86 anti-clockwise. That is the result. Now using that, we can finally find out the bending moment in all the portions and draw the bending moment diagram. I am not attempting that much over here. So this is how we apply the flexibility matrix method to a frame, a typical example of that. And that is the end of this section.